So the tool that we use to look at this is Elvis. So we've already heard a little bit about Elvis. So it stands for Exploring the Local Volume in Simulations. And this is something that Shay is leading and has done a lot of work on. So the reason I wanted to use these simulations is because they give us two things. One is high resolution, and we need this to look at dwarf galaxies in the Milky Way. And also there's a lot of them. There's 48 halos. Half of them are in this kind of local group environment. The other half are just mass-matched analogs. But if you think about this is similar resolution to, say, the Aquarius halos, which were these really ultra-high resolution dark matter. This has 48, there were 6. So this gives us the ability to both have the resolution, but also the statistics, which are needed for a lot of the questions we want to ask about dwarf galaxies. So, before going to kind of the results of this, I'm going to make some definitions, and I'm going to apologize from the start that I'm bringing up this abundance matching thing. From this morning, this is opening a can of worms, but for my purposes, I just kind of want a rough proxy between peak mass and stellar mass. I'm fully aware at these low mass scales this is highly uncertain, but I think just go with it for the purposes of this talk. So I'll be using the relation that Shay actually got from his simulations. This plot is showing this. This is a number of dwarfs as a function of stellar mass. It's showing the abundance matching prescription that Shay calibrated with local observations. And what this really means for the purposes of this, when I'm talking about major mergers, is if we use our fiducial definition of a major merger mass ratio greater than 0.3, this abundance matcher would correspond to a stellar mass ratio greater than 1 to the 10. So really this ratio really depends on what we're assuming, but for now we're just going to go with a major merger is greater than 0.3. That corresponds to a stellar mass ratio greater than 0.1. And I've kind of blanked out all the caveats that go along with this. All right. So the main first question, very basic question that we wanted to ask in these simulations is how common are mergers between dwarfs? Okay. And this is a plot showing cumulative fraction as a function of time of last major merger or redshift on the top axis. So there are three main things from this plot. The solid lines are for satellites today, so redshift 0. So this would be like the Milky Way type satellites. The dotted lines are what you'd call field dwarfs. They're not really, they're still in the kind of local group environment, so less than, say, a megaparsec, but they're outside the Vera radius of, say, the Milky Way. So, and the different colors and the different mass bins. So the first thing is that quite obviously, you get more major mergers at earlier times. This kind of just follows on from what we know about structure formation. Mergers are more common for more massive dwarfs. Again, that's not particularly surprising from what we know at larger mass scales. Maybe not quite so obvious is that mergers are more common for non-satellites. So in, like, say, the field, there are more mergers, more recent mergers than there are if you're a subhalo inside the Vera radius. But to put some kind of number on this, if you think about Fornax, which is about a 10 to the 7 stellar mass dwarf, and you believe the abundance matching prescription that we've used, about 10% have had a major merger since redshift 1. 10% is not that small, right? 10% is something that I think you kind of maybe want to worry about. And I think this is a rough number, but this is saying that maybe we need to start thinking about major mergers. Maybe not on the really low mass scales. If we go down to ultra faint, Draco, further down, these fractions become smaller and smaller. We're talking about the more massive dwarfs, Fornax and M31, and also Milky Way. This sort of mass scales, maybe we should start thinking about it. So as well as how common they are, something that's an obvious question is when and where do they happen? Okay. So when a major merger happens, is one thing that we wanted to look at in terms of satellites is they're a satellite today, but the merger didn't necessarily happen whilst they were a satellite. So what this plot is showing is showing fraction of things that merged before or after infall. So the red line is the fraction that merged before infall, and then the blue is after. So what we can see is that for the majority of times when mergers happen, the mergers that happen before they become a satellite. So the mergers that happen in the field. Only really at very recent times there's a switch over, and here like the number of mergers is very small and the statistics are very low. This is a couple of interesting consequences. When we tend to think about mergers between dwarfs, we think about dwarf spheroidals in the Milky Way, we think it's just colliding two dwarfs which are all stars, they have no gas, but maybe that's not the right picture to have, because when a major merger may have happened on these mass scales, it probably happened in the field, and at that time they may have had gas. Okay? So maybe we need to start thinking about wet mergers rather than dry mergers and the consequences that this may have. So this is speculative. I'm using a dark matter simulation, but I think this is something that would be neat to look at if we could at this resolution hydro simulations. But even so, the difference in wet and dry mergers may be important. So I said that mergers after infall are not super common, and that's true, they're not. But how do they happen? When you're inside the Vira radius, it's virialized, things are zipping around quite fast. How do like two dwarfs just randomly collide together? And the answer is actually it's usually not that random. We went back and looked at all these mergers that happened after infall, and we said, what were they when they crossed the Vira radius? And at all kind of mass range that we're talking at, about 70% actually came in as part of a group. So this wasn't most of the time it wasn't some random interaction. They came in as a group and then merged quite shortly after they crossed the Vira radius. So in terms of mergers, it's not common after infall, but if it does happen, it's likely related to group infall. And that kind of brings me on to something else that we're currently looking at in preparation, the statistics of group infall in general. This is obviously important for mergers after infall, but in its own right, it's quite an interesting thing to look at. So like I said, this is work in preparation, and Andrew, I'm sure, is busy working at this as I speak, writing this paper. So one thing that we looked at, this is a plot just showing fraction as a function of stellar mass. So the black line is just the fraction of dwarfs that were in a group at infall. And then what it's broken down to in the red and the green is, so red is that it was a satellite, and green is that it was actually the central. So unsurprisingly, at the lower masses, these are more likely to be the satellites rather than the central. But there's a kind of interesting number here. If you go down to like these lowest masses, this is saying around ultra faint sort of masses, 30% came in as a satellite of a satellite. And that is definitely not a small fraction. It drops down more to the classical dwarfs, but even there, it's quite a high fraction.
So
which was surprising.
The group is just in the virial radius?
Yes. Yeah. So this has some consequences which maybe we can probe observationally. So what this plot is showing is fraction of the things that came in as satellites as a function of where they are in the galaxy today. So the colors again are different mass scales. So if you look at kind of Milky Way satellites, kind of low mass systems, there's this sort of radial bias. So for the satellites of satellites population, there's a bias towards smaller radii, which is this is different from the overall subhalo population. And the reason for this is that they came in as a satellite of a more massive dwarf. And we know, like from dynamical friction, these things get dragged into the center. So this actually drags in these satellites themselves. This causes this radial bias in the distribution. So one thing, this is actually quite testable. We can look at the radial distribution of dwarfs in the Milky Way. The lowest mass scales at the moment, this is quite difficult because we can't find ultrafaints really far out. But if we could control those systematics and maybe in the future actually be able to go far out, we can actually see what their radial distribution really looks like. And the implication is that how centrally concentrated they are is going to tell us something about how prevalent satellites of satellites are. Okay. So that's kind of just the simulation side of it. But I want to briefly kind of link this to observations and something that has very recently come out that we've looked at related to this. So what we found in the simulations that satellites to satellites at the lowest mass scale should be quite common. Okay. So one thing we want to do is observationally try to find these things. And something that I think is important is not just to look at the surviving satellites in our galaxy, but also look at the things in the stellar halo that are now destroyed. Because these were also once dwarfs at some point. So in this paper that's recently been submitted to monthly notices, we made a link between different structures in the Milky Way. And for those of you who aren't a big Milky Way buff, the triand overdensity is probably not very well known. It was discovered about 10 years ago, I think, and it's probably as massive as, say, Sagittarius, the Sagittarius dwarf galaxy, but it hasn't been studied as much just because of where it is on the sky. But what we found in this paper was that the line of sight velocity of this structure, its distance away from us, and its position on the sky were all coincident with two other structures in the Milky Way. One being a narrow stream called the Panda stream, which was recently discovered by Nicholas Martin, and also the Segway 2 satellite. So for those of you who don't know, Segway 2 it's kind of been dubbed the lowest luminosity galaxy. Okay? And what we find in this paper is that it's likely that this very low luminosity galaxy is a satellite of a satellite, or was a satellite of a satellite when it fell into the Milky Way. And it may be related to this triand overdensity. So this could be evidence of like a fossil record of group infall into the Milky Way. And I say this is really just the tip of the iceberg, because we're looking, we're only using line of sight velocity. In the near future, we're going to have 3D velocity for a lot of structures in the Milky Way. And I think this is going to be key to piece together these different things. And I think trying to link the survivors and the failures in the Milky Way and seeing if they're connected in phase space is going to be, with comparison to simulation, something that we can do to try and figure out this satellite population. Okay. So I'm going to summarize all this stuff. First of all, dwarf-dwarf mergers are not negligible. They're not super common, so we don't need to go crazy about it, but they are something that we probably shouldn't ignore, especially on the sort of Fornax mass scale. I want to emphasize that they're more common in the field. And it's kind of an interesting consequence to it, because when we think about satellites of the Milky Way, we tend to worry about the environmental effect of being in the Milky Way halo. And one way to counteract that is to just go further out in the local group. Okay, this is where it's less likely to interact with a large host. But it's actually these ones, the ones furthest away in the field, which are more likely to have had recent major mergers. So it's just a kind of a cautionary tale about when we think about things that have interacted or not. If mergers do happen, and inside the virial radius it's rare, it's likely related to group infall. And whether the mergers happen before or after infall, I think may have some interesting implications of whether they're wet or dry. This is pure speculation because we're only looking at dark matter only, but it's something that should be explored in the future. When we looked at sub-halos or satellites of satellites, if we go down to the really low mass scales for, like, say, ultra-faint dwarfs, this is going to be significant. So when we want to understand these tiny little things, this is something we need to think about. There are special things about these ultra-faints. Some of them have weird tidal features. They have weird metallicity spreads. Some of these things maybe we can reconcile if we think about group pre-processing. And at the scales we're talking about, maybe this is important. And I think it's kind of an open question of how these things, how being a satellite of a satellite may have affected their properties. And finally, looking for evidence of this in the Milky Way, I think with the future surveys that are going to happen, like Gaia, this is going to be a real ripe thing to look at in the data. I think comparison with things like Elvis, these sort of simulations are going to be key to do this. I would argue that the best place to look for satellites to satellites in terms of phase space is going to be near massive dwarfs, either the ones that have been destroyed or the ones that are intact. These are the ones that likely dragged in several smaller mass dwarfs with it. And I think with that, I'll stop there. Thank you.
Thank you. So I just wanted to kind of reiterate what we heard this morning and what you pointed out. The halo mass stellar mass relation is really steep and probably has a lot of step.
Yeah.
And so my question is, what difference does that make? but then it's also, it's wanting to emphasize a 10-to-1 luminosity ratio, which normally we think of, who cares, is likely to be a major merger in terms of the mass ratio modulo the uncertainties in the slope and the scattering. So you say, well, it's not necessarily a big deal, but it's actually what you see in the sky may not necessarily correspond to the mass ratio that the galaxy's experiencing as well as one would just imagine in observer land.
Yes. So I think one thing I should say is a definition, right? How do you define a major merger? And that in itself is pretty arbitrary. Changing the stellar mass-halo mass relation will change the relation between, when you go from peak halo mass ratio to stellar mass-halo ratio. So, but one thing to emphasize is even if, you're saying it's 10-to-1 in stars, but it's 1-to-3 in dark matter, is that still important as a major merger? I mean, maybe if you're thinking about different stellar populations, but the impact of having a massive dwarf with maybe it doesn't have much stars, there's been recent papers showing that even if you have a dark dwarf and that merges with something with gas, that's going to have an effect. So really understanding that, I don't think it's clear. So I think, I totally agree when I'm talking about stellar masses here, I'm fully aware of this low mass regime, it's very uncertain and this can change the numbers for sure. This is kind of exploratory, and I think, it's just the first step.
Do you worry that cusp versus core will affect the survival lifetime of these?
Cusp versus core survival. You mean in terms of?
In terms of what faction will emerge before versus after?
Before or after infall?
In other words, if the dwarf survives longer than if the satellite survives longer, then it will more likely emerge after the satellite has come the way versus before.
Yeah, so in terms of the timescales, I think, are you talking about into the host halo or the interactivity?
Into the satellites.
Into the satellites.
Yeah.
So I should say that when we do our merger ratio, when we define a major merger, we define it when the dark halos are completely coalesced.
Right.
So that the kind of offset between first infall into a satellite is kind of, we just have it when they're completely gone.
Right.
So it's kind of a good proxy for galaxy.
If that happens sooner, you have a core versus a cusp, right?
Maybe. I mean, I think, that timescale could change for sure. I mean, I think the effect of baryons could change these sort of timescales too in other ways, right? So I think, that the kind of the x-axis, can shift for sure.
Okay. Are there any satellites that are still down? Like, did you see any that are actually still down to their roll?
That's a good question. And I think actually we haven't looked at it. I mean, we've kind of this is kind of the starting looking at this. One thing that I really would like to look at is relating something that's a satellite with a satellite when it fell in, and where is that today? Because if we want to link this observationally, we want to know, I'm sure phase space is going to be the best way to link these. Observationally at the moment, if we're just doing one velocity at distance, position on the sky, things could be completely, they may be related to angular momentum or something. But that link, I think, is going to be key using simulations to do that.
I think there is some evidence that Carina, I think it's Carina, has this subpopulation that people have claimed is actually another dwarf.
Yeah,
It's
the
bounced
cold
with.
thing, yeah.
Yeah.
Yeah. So there's kind of lots of these things, there are things that people have tried to relate streams to each other, Sagittarius, some dwarfs to it. There's lots of these kind of, and I think really the step forward in this is going to be having the multi-dimensional phase space to do it.
The question is why they didn't die by dynamic friction. Why did they merge? That is a theoretical question. A very hard question.
So when I say satellites to satellites, it's in the same way as you define a satellite in a Milky Way halo. So there isn't a strict, a velocity difference or a spatial difference. You can play around with that and how you define it. So really, you're right. I mean, it could be something quite loosely associated, but how associated it is kind of, at the moment, it's just based on the subhalo finder. But really, I think when we want to go to observations, we probably want to have a velocity offset or something to kind of make it more observation accessible.
Okay, thank you very much. Next talk.